Hi, I'm Sarah, and today we're going to be talking about the ideal gas law. This is the ideal gas law, and it explains the behavior of a given amount of an ideal gas. The ideal gas law is pressure times volume is equal to the number of moles of gas you have times the universal gas constant R times temperature. R is the universal gas constant, and it is expressed in units like these ones down here, where you have pressure times volume over moles times Kelvin. Pressure and volume can be in a variety of units. We're going to use atmospheres times liters, but in other cases you will use other units, and you'll need to make sure that the R you're given correlates with the units in your problem. So, assuming that we're going to use atmospheres and liters, let's lay out the units of the universal gas law and cancel them out so you can see how it works. Units of pressure in this case are going to be in atmospheres, and units of volume are in liters. Those are going to be equal to moles. Your units of moles will always be in moles. There's not a variable units for that. Here we have the units for R, atmospheres times liters over moles times Kelvin, and temperature will always be in Kelvin. If we cancel out our units, we see that moles cancel and Kelvin cancels, so we're left with atmospheres times liters equals atmospheres times liters. And that is what we want because those things are equal to each other. Now we can move on to actually use this law. The volume of a human lung is about 6 liters. Let's say that you breathe at 1 atmosphere and body temperature, which is 37 degrees Celsius. How many moles of gas can a human lung hold? First, let's make sure that everything is in the right units. We're going to use R equals 0.8206 atmospheres times liters over moles times Kelvin. So these are the units we're going to need in our problem. We have liters, we have atmospheres, but we have Celsius. So we're going to need to convert Celsius to Kelvin. How we do that is 37 degrees Celsius plus 273.15 equals 300.15 K, because 0 degrees Celsius is equal to 273.15 Kelvin. So now this is our temperature unit, and that is in the kind of units that we want. So we can set up the equation. The gas law is PV equals nRT, and we want to get N on its own because we're calculating for moles. So we're going to divide both sides by RT. They cancel out here, and we're left with PV over RT equals N, which is the equation we're going to need. Before we actually do the math, let's check our units. We have pressure in atmospheres times volume in liters divided by the universal gas constant, atmospheres times liters over Kelvin times moles times temperature in Kelvin equals moles. Now we have a fraction on the bottom here with our universal gas constant units. You should know that multiplying anything by like 1 over 1/2 is the same as multiplying it by 2. So what that means is we can take this fraction off to the side, and since it's in the denominator, what we have is 1 over atmospheres times liters over Kelvin times moles, and that's equal to Kelvin times moles over atmospheres times liters. So let's erase Kelvin times moles over here and move it up here. We can cancel these things out now. We have atmospheres and atmospheres, liters and liters, Kelvin and Kelvin. We're left with moles equal to moles, which is exactly what we want. Now let's plug in some numbers. I'm going to erase this so that we can replace it with actual numbers. We have pressure, 1 atmosphere, times volume, 6 liters, divided by the universal gas constant in liters times atmospheres over moles times Kelvin, and that is multiplied by 300.15 Kelvin in the denominator. And if we do all of that math, you'll get 0.243 moles. That's how much your breath can take up. But if you remember, we only had 1 sig fig up here. We only had 6 liters for our lung because it's an average of the human lung, which means that we're going to have to go back and get rid of a couple sig figs, leaving us with 0.2 moles. That is the number of moles that an average human lung can hold. So what if that average human lung exhales in January? It's negative 10 degrees Celsius outside and atmospheric pressure. How many liters, how much volume does your breath take up? Again, let's check our units. We are going to carry over 0.2 moles from the previous problem. We have atmospheric pressure, so that's going to be 1 atmosphere. We have our answer is going to be in liters, so that's what we want. But again, we have temperature in Celsius, so we're going to need to take -10 plus 273.15 to get 263.15 Kelvin. Okay, now we have all of the units that we need. And remember your universal gas constant, 0.8206 atmospheres times liters over moles times Kelvin. The gas law, PV equals nRT, and this time we want to get volume on its own. So we're going to divide both sides by pressure, cancel out, leaving us with V equals nRT over P. I'm not going to cancel out the units this time, but I highly recommend going back through and making sure all of your units canceled just like we did the last time. I'll do it briefly as I'm writing out the numbers. So our answer is going to be in liters. We have 0.2 moles, which is what we found in the last problem, and 0.08206 atmospheres times liters over moles times Kelvin times 263.15 Kelvin, and all of that is divided by 1 atmosphere of pressure. Quickly, I'll cancel out the units. Atmospheres cancels with what's in the top. We have moles here divided by moles in our gas law, or our gas constant, Kelvin in our gas constant multiplied by Kelvin up here. So we're just left with liters equal to liters, which is exactly what we want. And if you do all of that math, what you'll find is that the breath that you exhale will take up 4.4 liters, but again, we only had 1 sig fig here, so we're going to say that that is 4 liters. So when you exhale on a cold day in January, your breath will actually shrink if we assume that it stays at the same pressure to take up less space than what was in your lungs. There, we've done 2 problems on the ideal gas law, and that is it for today.